everybody. Today we're going to go through our last topic in Unit 1, 1.5, Inclined Systems. So today we're going to be talking about objects and systems of objects on an incline and how we deal with breaking down forces in that situation. So here we have a block that is sitting on an incline. Let's assume that it's a rough incline and it's stationary. So for a stationary block on a rough incline, what forces are acting on this block? So we've got gravity pointed straight down. Friction opposes motion. I know it's not actually moving, but it wants to slide down the ramp. So friction is going to oppose that. And the normal force has to be perpendicular to the surface. So at a 90-degree angle to the surface, our normal force. So previously, if we wanted to break this into components, let's say we had our y-axis here and our x-axis. We have friction at an angle. We have the normal force that looks like a different angle. Only gravity or the weight is pointed along the y-axis. And that seems like a headache to me. So what we can do instead is actually tilt our axis. Because our xy axis is just a reference. So we can tilt it however we want to as long as they are 90 degrees to each other. So if we tilt our axis like this, oops, so that the frictional force and the normal force are in line with our axes, then all we have to do is break the weight into different components. So that's what this little note here says. So on an incline, we're going to tilt the xy axis. So the x-axis is parallel to the incline. You can kind of draw that here. So if we have an incline, our x and y axis can just be tilted. So let's break this weight into components. So let's say our incline is at some angle theta. Through the magic of trigonometry, this angle here between the y-axis and the weight is also theta. So this angle right here. So the weight will have a component that is down the negative y-axis and a component that is down the negative x-axis as well. It's going to get a little bit messy here. This is our x and our y. So we'll have a sine component and a cosine component. So this adjacent side along the y-axis will be our cosine component. And along the x direction here will be our sine component. That's backwards from what we've seen so far. Usually we associate cosine with x and sine with y. So this is going to be flipped just because of where this angle is. So let's look at the sum of forces for this specific scenario. We'll have different forces in different scenarios. So what we're going to write here isn't a rule all the time, but let's break it down. So I'm just going to draw my forces again so it looks a little bit neater. So we got our normal force. We have our force of friction. And I'm just going to go ahead and break these components in just to draw them so I don't have this angled weight here. So opposing the normal force, looks like we have our cosine component, and then pulling down the ramp, which is why this block wants to move in the first place, is the sine component. And again, this is my x direction and this is my y direction. So looking at the sum of forces in the x direction, force of friction is pointed towards that positive x direction minus that sine component of the weight. And in the y direction, we have the normal force minus the cosine component of the weight. So for this situation, let's say I wanted to figure out what the normal force is. The sum of forces in the y direction would equal 0. We would set these two forces equal to each other. So the normal force is not going to equal the whole weight. It'll just equal the cosine component of the weight. Let's do an example. All right, so we have a 4 kilogram box sitting on a rough ramp with that coefficient of friction. It's a 30-degree angle pulled by a 50 Newton force. What is the acceleration and in what direction? So let's go ahead and draw our other forces. Let's assume it's being pulled up the ramp. So I've got friction opposing that motion. I've got my normal force perpendicular to this 30-degree angle or 30-degree incline. And then weight is pointed straight down. I'm drawing it from the center just so that I can draw my triangle a little bit easier. So I've got my y-axis and my x-axis here. So I'm going to break this weight into components. So I have part of the weight is pointed into the ramp. That is my FG cosine 30 component. And then part of it's pulling down the ramp. That's my FG sine 30 component. So first let's deal with the y direction, because I know that the sum of forces in the y direction will be 0. This is not accelerating off or into the ramp. So sum of forces in the y direction will be 0, which means my normal force is going to be equal to FG cosine 30. And I know that the mass is 4. FG, I have to multiply that by g, so let's say that's 10 times the cosine of 30. And that gives me a normal force of 34.6 newtons. Let's look at the sum of forces in the x direction. It's accelerating, so my sum of forces equals mass times acceleration. I have a 50 Newton force pulling up the ramp, and I'm going to be resisted by the force of friction and also this sine component down here. So two forces or components are resisting that pull. Cool. Recall that the force of friction is the coefficient times the normal force, so I'll substitute that in for the friction. So 50 minus 0.4 times 34.6 minus the weight, so 4 kilograms times g, round that up to 10, equals 4 times our acceleration. Subtract all those things, and we get about 16.16 equals 4 times my acceleration. Divide everything by 4, and we get 4.04 meters per second squared is my acceleration.